Hi, everybody. My name is Samuel Horvat, and today I'm going to present you our work titled Fed Shuffle, Recipes for Better Use of Local Work in Federated Learning. The outline of my talk is following. First, I'm going to discuss Federated Learning, its motivation, introduction, and challenges. Then I will discuss the way how to tackle statistical and computational heterogeneities with a particular focus to better understand practical traits that people usually use in practice. And then I will conclude and discuss future work. Okay, so let me start with federated learning, FL for short. Traditionally, in machine learning, we implemented intelligence by collecting all the data in this one centralized location. Over the time, we moved from local solutions to cloud-based solutions, as much machine learning success relies on large-scale training infrastructures and the vast amounts of training data stored in one centralized location. But there is a downside to this procedure of the centralized setup, and this is that data usually comes from users, and this collection can hurt user experience, mostly due to privacy implications. To protect users' data, the privacy were already enforced by both government entities and by private companies as well. These regulations will eventually lead to limited availability of data. So now the question is, what should we do to actually still use decentralized data while also respecting user privacy? And this is where federated learning comes into play. So federated learning is defined as machine learning setting, where we have multiple parties that want to collaborate in solving a machine learning problem. And this collaboration is coordinated by a certain server. The core idea of federated learning is a decentralized learning, where the user's data is never sent to the server, actually never transferred or exchanged. It is kept only locally, and instead, the learning objective is meant to be achieved using focus updates intended for immediate aggregation to avoid any privacy leaks. So at least it gives us this hope to train on large decentralized dataset while keeping data private. In addition to that, there is an increasing demand to obey data locality paradigm, which means to process data where they are stored. And also there are several recent studies showing that federated learning can be actually greener technology than cloud-based training. Regarding its application, federated learning has been already used in several commercial applications such as Apple's Hey Siri or Google's Hey Google. On the other hand, federated learning is still a relatively new concept. There's definitely more to come in the future, particularly it can be very useful in applications where we historically wouldn't have that much of data due to data privacy issues such as medical or banking applications. Regarding the settings in federated learning that we usually consider, there are two main settings. First, there is a cross-silo setting where a number of companies or organizations, they share a common objective to train a model based on all of their data. But the issue is that they cannot share data directly with their, for instance, hospitals. Another setting is cross-device federated learning, which is a setting where training happens within the server. And clients are different mobile phones or IoT devices. We have many such clients, but by many, perhaps you have millions or even hundreds of millions of clients. Each device has a small amount of data, and they want to collaborate in order to train prediction model or recommendation model of some sort. And once this model is trained, it is to be used on device. Unfortunately, as such, federated learning comes with several specific challenges that need to be addressed. Among them, one of them is communication being a bottleneck. And the problem here is that communication is expensive in federated learning. And this is due to two main reasons. Firstly, this is because wireless links and other end user internet connections are much slower than data center links. And it should be also noted that even scaling might be even a problem in data center communications. And secondly, this is due to the limited capacity of the aggregated master. Especially the cost of communicating updates is a key bottleneck. There are several ways to fix this problem, where standard approach is to reduce communication by reducing the size of the communicating updates. Another very popular approach that is focus of my talk is allowing each client to run multiple local updates before communicating back to the master. Finally, the less standard approach is to do importance sampling for federated learning, which means to somewhat smartly limit the number of devices that communicate with the server. What I would like to stress here is that all these three approaches commonly constituted in literature are orthogonal and can be combined for improved overall effect. All right, so let us first look at what kind of objective we optimize in federated learning. So we optimize the following objective where we have n clients. Each client has its own local data set and local loss. It can be written as an empirical risk minimization problem over its own local data set. And then where each client loss is then weighted by some value, typically proportional to the size of the local data set, such that globally we recover the global empirical risk minimization problem over the whole data set. The common way to solve such objective is to employ federated averaging. And here I'm going to introduce its practical implementation as introduced by McMahon and his co-authors. So firstly, what happens is that the server sends a global model to all available devices. These devices then perform one or several epochs based on their local data, and then they update the model. The model update is communicated back to the server, which aggregates them, and lastly update the global model to be distributed in the next round. In the paper, we conclude the detailed analysis that discovers that there are two particular issues with this algorithm when data are not balanced. Namely, this is caused by running local epochs and the way the standard aggregation is performed. For the local epochs, heterogeneity in number of updates per client can caused by this unbalanced data set leads to objective inconsistency, meaning that we actually end up optimizing different objectives than originally intended. And here, what we do, we visualize this problem on the simple 2D quadratic objective, where what you see is actually when you run more local steps on particular clients, then the actual solution that we converge is attracted to the global solution instead of, to the local solution of that given client instead of the global solution that we're trying to find. There are two ways to fix this. So we are not first to realize that there is some issue with that, but Wang and co-authors, they proposed to actually rewrite the updates to remove the objective inconsistency. What we did in our work, we proposed to actually instead rescale step sizes such that we balance the updates. And we showed that it's also removed the objective inconsistency, but it has an extra advantage that it enables for larger theoretical step sizes. For the aggregation, the problem is that the proposed ways, the originally proposed ways are of the following form, which you might find simple or maybe even intuitive, but actually it turns out that it causes objective inconsistency as the weights are not really consistent. And in addition, they are not very even compatible even with uniform sampling of clients for which this was originally intended. In our work, we propose a simple fix to this issue by just aligning the aggregation weights with the client sampling. We show that this completely removes the objective inconsistencies as probabilities once you take expectation, the simple cancels out. On top of that, there is another challenge that has to be properly taken care of, which is that practical implementation of federated averaging contains random reshuffling or so-called without replacement sampling. So the difficulty comes from the fact that for random reshuffling, we do not sample from a full data set in each step, but only from the subset that has not been sampled yet in a given epoch. So such sampling can intuitively reduce the overall variance, as in each epoch we see every single data point, but it also leads to bias updates and it introduces a more challenging theory, unlike this with replacement sampling that I display here on the left. To put everything together, we designed a generalized federated averaging algorithm that we name FedShuffleGen that contains all of the aforementioned ingredients. So this would be namely, it allows each client to run different number of local epochs. It allows for partial participation here with this that's represented by the sampling denoted by calligraphic S, meaning that only subset of clients participates in each round. We also give a freedom in selection of local step size, and also we give a freedom on how the aggregation weights are performed. So by analyzing this algorithm, we showed that based on the parameters by which we parameterize our algorithm, the actual objective that we end up optimizing is of the following form. So where the difference to the original objective is that this VIs with hat, they do not really need to correspond to the VIs of the original objective. And this is what creates this objective inconsistency. And these VI hats depend on the selection of the parameters that we consider. So the nice thing about this general algorithm is that as a byproduct of analyzing this very general algorithm, we also obtain the first analysis of practical implementation of both Fed averaging and FedNova, which are popular methods for federated learning, as these become actually the special cases of Fed shuffle gen for particular choices of parameters. And what we discover is that Fed averaging has, as implemented in practice, introduces this certain inconsistencies that I was discussing in prior slides. Furthermore, this freedom in client sampling, it allows us to choose static sampling that leads to a faster convergence rate if we have control of the sampling of the client. And also finally, we can choose such parameters that leads to the best convergence rate while not introducing any objective inconsistency. And this led us to our newly proposed method that we called Fed shuffle. So for Fed shuffle, we employ step size scaling. Also our consistent aggregation to remove objective inconsistency. We employ random reshuffling to reduce stochastic gradient, variance of the stochastic gradients. And also we play with the global and local step size to optimize convergence rate. This method enjoys the following convergence rate under the standard assumptions, including smoothness and strong convexity, gradient similarity, and bounded variance. In the paper, we also provide convex and non-convex rates. Regarding the notation, R stands for the number of communication rounds. E is number of local epochs performed by each client. Smoothness is denoted by L. Then U represents strong convexity. And M is the sampling parameter. Eta G is a global step size. If we look at the obtained rate, it's tied when compared to the previous work. For instance, when compared to the best known rate for standard Fed averaging, where we obtain better dependence on the variance term, which is the middle one, with respect to number of communications around R. But unfortunately, it turns out that we do not really get any improvement when compared to simple baseline distributed gradient descent, which actually rate is equivalent to ours without the middle term. The problem is that client drifts towards the local data when performing local steps. And what I would like to stress here is that this is really consistent with prior literature and known lower bounds. One interesting direction that we would like to look for the future is incorporating random reshuffling of clients, actually improve the dependence on the on R in the first term. All right, so now the question is how to reduce the client drift in the rates that I showed you before. So typical approach to reduce client drift is to employ variance reduction, meaning to provide clients with some kind of a global direction that reduces the local client drift. In our work, we decided to follow the momentum variance reduction of Chutkowski and Orabona and Karimiridi and co-authors, where what we employ is that this local direction DIJ is enhanced with this momentum, and then extra error term. Or what you can note here that the global momentum is updated only once per communication round to make sure that it points to the global direction. What we show is that under standard assumptions, or with an extra assumption on Hessian similarity, we obtain the following convergence rate. The Hessian similarity here can be seen as an extension of smoothness assumption, as displayed here, where smoothness can be seen as an assumption on the second moment, while Hessian similarity captures more variance with respect to the Hessians. When we compare these results to the baselines that do not perform any local steps, what we observe is that we obtain the dependency on delta, so on the Hessian similarity, instead of the smoothness parameter, which can actually be in practice much smaller if the data set are somehow similar. In the worst case, it's less than 2 times L. And what I want to stress here that this result is actually consistent with the prior work that analyzes only balanced data set with replacement sample. All right, so let me just showcase you some of the experiments that we concluded. So we start with the toy experiment to showcase our theoretical results. We optimize simple quadratic objective as displayed here. So for the baselines, we consider federated averaging and FedNova with and without random reshuffling. And our proposed baselines, Fed averaging min and Fed averaging mean, that runs the same number of local steps per client to avoid objective inconsistency. So Fed averaging mean runs the minimum number of steps comparing to clients who run Fed averaging, while Fed averaging mean runs average number of local steps per when compared to what standard Fed averaging would run. So for the first experiment, here the Fed shuffle algorithm is displayed in brown. And what you can note is that it always is the best performing methods. And what you can also note here when compared to other methods that each component is important. So for instance, what you can note here is that random reshuffling boosts the performance of FedNova, where we have FedNova with random reshuffling versus FedNova here displayed in red without random reshuffling. And also what you can note here is that Fed averaging does not converge to high precision, and this is due to objective inconsistency. And what you can note here that for all methods, momentum reduces variance and therefore improves the quality of the solution that to which we converge. For the second experiment, we take a closer look at the aggregation step. So what we show is that Fed shuffle with standard aggregation rule here, it shows the standard aggregation that people usually deploy for Fed averaging, here denoted by SO. It actually converges to worst quality solution when compared to our proposed sampling. So we're compared to our proposed sampling aware aggregation strategy here displayed in blue. Also, on the right, where you can note here that if we have control of sampling and we can actually employ imported sampling, it leads to an improved convergence speed, as you can see here. So for the more real-world experiments, we consider 2 tasks. So first is next word prediction on Shakespeare dataset that consists of 715 clients, and then also on we consider a balanced cipher 100 with 500 clients that were obtained using from the cipher 100 dataset using Dirichlet allocation. And for the baseline, we use exactly the same as before, with the difference that here all methods employ only random reshuffling, as this was shown to be practically superior method, and that is whole motivation why we actually analyze, why in our work we analyze this random reshuffling. So what you can note here that for unbalanced Shakespeare data set displayed on the left, we can see that relatively large gap between performance of Fed shuffle displayed in purple and all other baselines. And here on the right, we have exactly the same baselines, but with momentum. And again, we can see that the momentum improved performance of all the methods, while our Fed shuffle is still the best performing. For the balanced data set, to model the unbalancedness, each client on this example runs 2 to 5 epochs that are sampled uniformly at random, so to model this difference number of local steps. And what we can see here that Fed shuffle still performs among the best, but the gap is significantly reduced, and this is because the methods becomes more similar, but and this is somehow expected and consistent with our theory. Okay, so let me here conclude. So in this talk and in this work, we propose and analyze Fed shuffle, which incorporates the practice of running local epochs with reshuffling in common federated learning implementations, while also accounting for data imbalance across clients and correcting for the resulting objective inconsistency problem that arises in Fed averaging type of methods. So Fed shuffle involves adjusting local loading rates based on the amount of local data, in addition to modified aggregation weights compared to prior work like Fed averaging or Fed NOVA. And under additional Hessian smoothness assumption, we show that incorporating momentum variance reduction leads to improved rates compared to non-local update methods. For the future work, we are interested in asynchronous execution, also incorporating compression mechanisms to reduce overall communication overhead. And also, we would like to extend our work to account for different computational and communication heterogeneity across the clients. Let me here acknowledge my wonderful collaborators, namely Maziar, Lynn, and Mike from Meta AI, and Peter from Cast. With this, I would like to conclude my talk, and thank you for your attention.